Welcome to the Greek Ship Corrosion channel. My name is Mariam. I'm a researcher in the field of corrosion and protection of materials. Chapter 1, Section 6. Reference electrodes. Number 1. Standard hydrogen electrode or SHE. Number 2. Silver chloride electrode. Number 3. Mercury chloride electrode. Number 4. Copper sulfate electrode. The references are shown here. Potential measurement. Reference half cells or reference electrodes are used to establish the relative potentials of metals in contact with aqueous environments. When metals or alloys are exposed to complex electrolytes, the reference half cell measures the corrosion potential. That is, the difference of electrical potential between the metal and its aqueous environment. This difference cannot be measured directly because the introduction of a measuring probe into the aqueous medium introduces another metal-liquid interface, across which an additional potential difference exists. Measuring relative quantities such as potential and height always needs a base or a reference. In this figure, the location of the dot doesn't change, but its height changes depending on the base. H1 according to base number 1, H2 according to base number 2, and H3 according to base number 3. Changing the reference or the base of measuring causes a change in the quantity. Thus, in order to measure a relative quantity, it is essential to determine the reference or the base of measuring. Any potential measuring instrument connected between the metal and the probe will indicate only a difference in potential, and absolute values of the individual half-cell potentials cannot be determined. This discussion shows that relative values of half-cell potentials are established if the measuring probe is a highly reproducible second half-cell. These half-cells are referred to as reference half-cells or reference electrodes. Standard hydrogen electrode. The accepted primary reference half-cell is the standard hydrogen electrode or SHE, consisting of platinum simultaneously in contact at 25 degrees Celsius with a solution of hydrogen ions at unit activity and hydrogen gas at 1 atmosphere pressure. This half-cell potential is assigned the value 0. Arrangements for making potential measurements. Schematic arrangements for measurements of electrode potentials using an electrometer are shown here. A. Circuit completed through a salt bridge between the reference electrode and the specimen electrolyte. B. Circuit completed through the specimen electrolyte. The working electrode or specimen potential is measured relative to the reference electrode. The working electrode may be a pure metal and it may be immersed in a solution containing its own ions, in which case the half-cell potential E' is measured, assuming that another possible half-cell reaction, for example oxygen reduction, does not significantly polarize the potential away from E'. In corrosion investigations, both the working electrode and the solution are typically complex in composition, and the corrosion potential E core established by simultaneous anodic and cathodic reaction at the metal surface is measured. Measuring electrode potentials using a salt bridge. The reference electrode contacts the working solution through a small opening. In Figure A, contact is made through a salt bridge, a tube frequently containing potassium chloride solution or the electrolyte of the electrochemical cell. Measuring electrode potential without using a salt bridge. The salt bridge minimizes cross-contamination by species in the two solutions that could alter the potentials of the individual electrodes. If cross-contamination is not a problem, The reference electrode is frequently placed directly into the working solution, as shown in figure B. What is an electrometer? The potential of the working electrode relative to the reference electrode is measured with an electrometer or high impedance voltmeter. This instrument must have an internal impedance large enough to limit the measuring current to values less than currents that can significantly affect processes occurring at the electrodes. For example, if sufficient current passes through the reference electrode interface, the reference electrode can polarize and shift its potential from the reversible value. Potential measuring instruments with measuring currents sufficiently small so as not to influence the reference electrode or working electrode potentials are generally called electrometers. These instruments should have an internal impedance greater than 10 to the power of 10 ohms, and frequently they have values greater than 10 to the power of 14 ohms. Why should electrometers have an internal impedance as high as 10 to the power of 10 ohms or more? The importance of having an internal impedance of this magnitude is illustrated by considering the measurement of the corrosion behavior of specimens having an area of 1 square centimeter, a size frequently used in laboratory measurements. A reasonably low corrosion rate of 25 micrometers per year or 1 mpy corresponds to a corrosion current density of approximately 10 to the power of -6 ampere per square centimeter for most metals. An externally imposed current should be less than 10 to the power of -8 ampere to be only 1% of the corrosion current. If the potential between the reference electrode and the corroding metal is 1 volt, the resistance of an electrometer should be greater than 1 divided by 10 to the power of -8, that is equal to 10 to the power of 8 ohms. This rough estimate plus other factors confirms that the internal impedance of an electrometer needs to be of the magnitude indicated here. Types of half cells: potentials of standard hydrogen electrode and silver chloride electrode. 0 for SHE and positive 196 millivolts versus SHE for silver chloride in saturated potassium chloride. Potentials of calomel electrode and copper electrode. Mercury chloride positive 241 millivolts versus SHE in saturated potassium chloride. Copper sulfate in saturated copper sulfate positive 360 millivolts versus SHE. Mercury sulfate in saturated mercury sulfate positive 621 millivolts versus SHE. Silver sulfate in saturated silver sulfate positive 654 millivolts versus SHE. Mercury oxide in saturated mercury oxide positive 98 millivolts versus SHE. 5 factors contributing to the selection of components and to the design of a satisfactory reference half cell. Number 1. The metals must have sufficiently positive half cell potentials that corrosive reactions do not occur. Number 2. The half cells identified as saturated have the advantage of more easily maintaining a constant anion concentration and hence half cell potential. Number 3. Reference electrodes are usually constructed as glass tubes containing the metal and the electrolyte. An opening must be provided in the end of the tube for ion flow. Number 4. A potential difference develops at the junction between the electrolytes of the reference half cell and the working electrode being measured. The junction potential must be considered when precise measurements are required. The liquid junction DC potential can be decreased by inserting a salt bridge between the solutions so that there are two junctions instead of one. Number 5. Sulfate and oxide types of reference electrodes are advised when chloride contamination is a problem. Structure of the reference electrodes. Schematic representations of saturated calomel electrode and copper sulfate electrode reference electrodes are shown here. Calomel is generally used in laboratory investigations, and copper sulfate is a durable and inexpensive reference electrode used especially for structure potential monitoring for cathodic protection. Fill hole, ceramic frit, porous plug are shown here. Thank you for your attention. Challenge number 8. If you like to challenge yourself, please answer this question in the comments down below. How do we convert the potential of a half cell versus standard hydrogen electrode to the potential versus saturated calomel electrode? Do you confirm the following potentials? E0 Cu2 plus Cu equals positive 342 millivolts versus standard hydrogen electrode. E0 Cu2 plus Cu equals positive 101 millivolts versus saturated calomel electrode. E0 Fe2 plus Fe equals negative 440 millivolts versus standard hydrogen electrode. E0 Fe2 plus Fe equals negative 681 millivolts versus saturated calomel electrode. The potential of mercury chloride in saturated potassium chloride equals positive 241 millivolts versus standard hydrogen electrode.